All right. Well, we also have an extended weekend. We get President's Day off, so you can enjoy your 3-day weekend, Valentine's Day and President's Day, and statistics and whatever other classes you're taking. So, all right. So today I'm going to introduce, I guess a machine learning technique where gradient descent is frequently used as a way to optimize what we're doing. Okay, and so I'll post up a kind of a series of videos that someone else made. They're very good videos, and then I'll also post up some reading for you guys to do on this. Okay, and so this is we're going to learn just very very basic, okay, artificial neural networks. All right. Okay. And is it just a fancy term for, I don't know, neural networks? I don't know what else we call it. Okay, so let's say, you know what? I forgot the data example that they used. But let's say we wanted to. So I'm going to just use the example that they have in the video, which is y is going to be a test score. And then our input will be, let me pause here for a second. Okay, so we're going to look at, we're going to have two inputs, which will be hours of sleep and then x2 will be hours of study, and then y will be our test score. All right. And then here we just have three observations. Okay, so you slept for 3 hours, you studied for 5 hours, your score is 75. You slept for 5 hours, studied for 1, and you scored an 82. Slept for 10 hours, studied 2 hours, and scored a 93. Okay, this is what the neural, this is the data that we're using, okay? And so basically we have two inputs and one output, okay? So we have, you know, there are a few ways to approach this, right? One way is to do multivariate linear regression. This is one way to do it, right? We have, you know, an x1 and an x2, and we're going to try to predict a test score. So, you know, one method you know, you've got, you know, you're going to have beta x1 plus beta 2x2 is equal to, you know, y hat, all right? You know, maybe a beta 0. Okay, something like this, okay? And you know, there's other ways to do it, okay? But what we will learn today, or what we will, I guess, introduce today, will be the artificial neural network, okay? Also called an ANN, okay? And basically what we have is, this is our input. This will be x1, x2, and out here we have our our y hat, our output. Okay, but then we're going to put in something called a hidden layer. Okay, and what the hidden layer does is we take each of our inputs. Okay, so x1 will get fed into each of these nodes here. Okay, so these are supposed to kind of mimic like a synapse of the brain, where you've got these things connecting to it and then spreading out from there. Okay, so each of these will connect, and then x2 also feeds into this, and this feeds into this, and this feeds into this. Okay, and then each of these things get put, they produce an output. Each of these neurons produce an output, and they feed into here, which then takes 3 inputs and produce 1 output. Okay. And the way it's going to work is each of these values. So the first time I'm going to plug in 3 for x1 and a 5 for x2, and they're all going to go to each of these. Okay, and they're going to be multiplied by a weight. Okay. I'm trying to remember the notation here. I'm just going to call it weight 1, weight 2, weight 3. And maybe this is not... okay. And so they each get multiplied by a weight. At each basically neuron here, or node here, we're going to take these 2 values and combine them. Okay, so this right here, we're going to have basically 3, for the first observation will be 3 times the first weight plus 5 times the other weight. Okay, and so this, basically our input is this thing, and then we apply a function to it. Okay, so we apply a function to our input. Okay, and so what gets output will be a function of 3 times W1 plus 5 times W4. Okay, so this is going to be our output. Okay, and then and the same can be said for the other neurons. Okay, and then so now we'll have 3 of these. So we can call the output of this first one, we can call this like Z1. Okay, and then so here we'll have Z1 coming in here, Z2 coming in here, Z3 coming in here, and then this output will be a function of Z1 plus Z2 plus Z3. Oh, I'm sorry. Those outputs, I got to go back. Hang on a second. Okay, so this will output Z1, but then we're also going to multiply it by another weight. Okay, and then so this will be an output, and we multiply it by a weight, and this will have an output, and we multiply it by a weight. Okay, so we can alter all of these weights, and so what gets fed into here will be a function of this output multiplied by its weight plus this output Z2 multiplied by its weight, and then the last one Z3 multiplied by its weight. Okay, and then we'll have another function based on this that's going to output Y. Okay. Okay, so and then we could complicate neural networks more by having like additional hidden layers. Okay, like you could have something like this feeding into a hidden layer, and then that gets fed into another hidden layer. Maybe even more, whatever. Okay, and then they all get fed into a whatever output we're looking at, or you could have multiple outputs, whatever it is that you're looking at. Okay, and you can build really complicated models. Okay, and if it's whatever. Okay, and you can have like a quote deep learning network. Okay, but we're not going to worry about that. Okay, we're just going to look at this kind of simple setup here. Yeah.
Do we really want to do linear regression on this? Because like phi1 and phi1 to phi3 are just functions of x1 and x2, and the functions are linear. So when you just multiply them, it's still linear. So
Correct. Yeah. So yeah, this is okay. This is the output of f is not necessarily a linear thing. Okay. So yeah, we have a linear combination of the weights going into this node here. Okay. But then the node takes those inputs and then spits something out. Okay. And so we have the most basic of these would be the perceptron, okay, which is basically a step function, okay, which we're not going to use, okay. So this could be this is the function of the inputs at a node. Okay, and so what this would say is, here along the x-axis, or I don't know, this will be kind of values of our input, which at our current state is what, 3x1 plus, or no, 3 times w1 plus 5 times w4 or whatever I have. I probably need to rename the weights appropriately. Okay, and this function basically says up until a certain point, which we'll call b, it's 0, and then once it reaches that point, it becomes 1. Okay, so this would be the value f of w. Okay. All right, and so while 3w plus 3w1 plus 5w4 is small, the output is 0, and then suddenly it jumps up to 1. Okay. And I don't know. You can do some like logic gates this way. Say. Okay, so we can build a a simple like a logic gate, which would be like if you wanted to build a so the example would be a not and gate. Not and gate is supposed to produce, right? So if your input is 0 and 0, 0, 1, 1, 0, 1, 1. These would all be 1, and that would be 0, right? Because you don't want the and. Okay, and so in this case, you would have 2 inputs and then 1 output. Okay, and so we can just say we can put in a 2 and a 2 and a this could have the function, you know, 1 1, and then is basically the function is 2x1 plus 2x2, is that minus 5? No, 3? What am I doing? 0 0. Okay, yeah, minus 3. Is this greater than 0? Wait, do I have this backwards here? 0 0, less. Okay, so actually I want it just the opposite. So I want these to be negative, negative, and positive, like this. Okay, and then so we can see, you know, if we plug in 1 and 1, I'll get negative 4, and that will be less than 0. And then if I plug in anything else, the result will be greater than 0, and so that would be a simple thing, right? So here, if x1, x2, kind of our function. So this basically, you know, it's a indicator. Is it greater than as a okay, so if this we have 0 and 0, 0, 1, 1, 0, 1, 1. So here I have negative 2x1 plus negative 2x2 plus 3. And then we'll have an indicator on is that quantity, which I'll just call z, is that greater than 0? So here I have minus, here I've got 3, here I've got 1, here I've got 1, and here I've got minus 1. So is this greater than 0? Yes. This is greater than 0, this is greater than 0, and this is not. Okay? So essentially we're taking our inputs, and then we're putting them, turning them into, you know, 1 and 0 outputs. Okay. So in this case, this is not the proper input here. Okay. So this would be this is a step function. Which could work in certain applications, but this is not ideal for the application that we want to do, because what we want to do is we want to eventually search the gradients to kind of find our optimum values. Okay, and so what we're going to do is use, rather than this step function, we're going to have kind of a logistic curve, which when we're in the literature, when we're talking about artificial neural networks, we this is known as kind of the sigmoid function, but it's basically it's like a logistic curve, and it's basically the function, let's say z, is going to be 1 over 1 plus e to the negative z here. Okay, and so you know, when z is very, very big, you're going to have 1 over 1 plus infinity, which I'm sorry, no, 1 over 1 plus 0, so this is 1. And then when z is very negative, you're going to have 1 over 1 plus infinity, and that's going to be 0. Okay, and it's only when kind of z is in this sweet spot range, when z is near 0, then you'll have 1 plus, e to some power, okay, e to the 0, so this would be 1, and you get something around, something in between 1 and 0, okay? And the advantage of this is that, we can see what a small change in our input can create a small change in our output. Okay. Whereas with the step function, okay, so like right here, if I'm at we'll call this z0, and I move up to z1, okay, this is associated with a, this is a large change, but it's associated with this change, right? So okay. Whereas on the with the step function, if I can go back, whoops. With the step function, if you're over here, okay, a small change in z produces no change, okay? But if your change happened to be right here to right here, maybe a small change here suddenly causes you to jump from 0 to 1, okay? And so you get these, the behavior is a lot harder to predict, okay? Whereas over here, you might get tiny changes or you might get substantial changes, but overall, if you're picking small changes in your input, that's associated with a small change in our output. Okay. Okay, let's hang on a second here. Okay, so going back to our neural network here, we can look we can kind of construct our copy our data over to so we can we can see that everything's kind of a function of our inputs, right? So we've got we can treat this as a matrix, right? So we can call this x1 and x2, and maybe I'll put, let's say, our first observation. So our input matrix of observations is like this, okay? And then we can see what we're going to get is going to be, we're going to multiply this by our weights, right? So we got, So, hang on. So I need 3 by 2, 2. So this will be weight 1, weight 2, weight 3, weight 4, weight 5, and weight 6. Okay. And so this multiplication operation is going to produce kind of our inputs, right, for this thing, which will be am I going crazy here? What's going on? So I got weight 1 x1 plus weight 4 x2 and then this will be weight 2 x1. So these are kind of our inputs for each of our each node, right? Why am I struggling with this? And there's no plus here. Okay, and then okay, so these are the inputs for basically our inputs for the hidden layer. Okay, so I'm going to have a 3 by 3 matrix, okay, because each we've got 3 observations going into three things here, okay, and then so then we can apply a function to this. So we can call this our kind of our z matrix, which is our inputs for the hidden layer. Okay, and then we'll apply the kind of that sigmoid function to our hidden layer. Okay, and then we'll get outputs there. Is this okay? So my pen. Etc. 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 And then W1 X1 3. Okay, so we'll have our inputs here. We got our matrix here. This is just with kind of 3 training examples, right? So these are the 3 inputs that we are using to say, hey, this is what our model should be able to predict. Okay, so so on the hidden layer, let me see if I can just copy this over again. So and then we're going to take our outputs of that z. Okay, so we have our z matrix, which basically has 3 rows and 3 columns. Each, 1 row per observation. And then here we got 1 column per node in the hidden layer. Okay, let me just. Okay, so that's so we have 3 rows and 3 columns. We're going to then feed that matrix into our function. Okay, this is our sigmoid function. Okay, so we're feeding in our matrix Z, and we're going to get output A. Okay, and so output A is going to be we're going to have yeah, it's going to be still be a 3x3 matrix. Okay, one row per observation, and 1 column per node. Okay, and then we're going to multiply this letter A by all of the weights here. Okay, so so after we apply, so basically A is going to be, you know, a function of kind of the first one, 3 plus 5 W4, et cetera, et cetera, et cetera. Okay. W2 plus 5W5. Okay. So we've got so we have this A matrix. All right, and then to get our inputs for our final node, we're going to then multiply this by our weights W7, W8, and W9. Okay, so here we have another matrix, and this is going to just be not plus W7. Okay, which in the tutorial video that I'll send you guys, the weights are numbered differently here. Okay. No, I have this. This needs to be a column. I'm sorry, not a row. Okay. All right, and so after you know, when we multiply this by here, we're going to end up getting a 3x1 matrix, right? So if I wish I could just so let me just cut this and just slide this over. Okay, so you know, when we multiply the results of applying the function to our Z matrix, we're going to get basically weight 7 times basically the output of 3W1 plus 5W4 plus, you know, the next weight times 3W2 plus 5W5 plus the last weight times 3W3 plus 5W6 or something like that. Okay? And then you'll have basically the same thing, W7 times basically observation 2 W9 of observation 2, and then you've got the same for you know, observation 3. Okay, but this is a 3x1 matrix. Okay, so 3 rows, 1 per observation. Okay, by 1 column. Everything okay so far? So, so just to kind of reiterate, we're taking our inputs. We've got two inputs, x1 and x2, and we are going to multiply those by weights into our hidden layer. Now, our choice of how many nodes to have in our hidden layer is arbitrary. You can have a bunch or you can have a few. We've chosen 3 for this simple example. So we multiply each of the inputs by our weights. Those become inputs into our hidden layer where we apply the function, okay, that sigmoid function, which takes our numeric input and produces a numeric output between 0 and 1. Okay? Those outputs we're going to call Z1, Z2, and Z3, which is basically what we have here. Our A matrix is, I'm sorry, not Z, this is the output of our Z. So after we multiply X by W, we put that in there, okay? This is, I guess I gotta say a function of this, okay? And so we're going to then multiply that by our next set of weights to get as a final set of inputs for our last function application, okay? So so we'll do that. Okay, so now we have a 3x1 matrix to apply the function to, and then we're going to add them up together to get our final output here. Okay. So to train our neural network, okay, we can modify the weights, okay? And so we have a total of 9 weights in our model. Okay, so that's because our output y, our output y hat is a function of the data and the weights. Okay, now the data that we provide is fixed. We can't really modify that. Okay, but we can modify the weights, and so so that's what we're going to do. Okay, and so what we're going to do is we have a cost function, and so the cost function is going to be the difference between our prediction and the kind of and the actual value here, okay? And we'll square it and we'll add them up. Okay, so this is kind of just like our, squared residuals almost, right? Squared error. Okay, and we often like to use squared error things for cost functions because things of quadratics are convex, which make searching for maximums or minimums easy. But if you wanted to choose a different cost function, that's fine. Okay, and so if we think about this, okay, we have our inputs and then we have our predictions. Our prediction, if we fully expand this, okay, we can fully expand the prediction. We can fully expand the prediction, and as a function of our data and weights. Okay, and really we'll treat our data as fixed, and that's what we'll do. Okay, and then so I guess on Wednesday, we'll apply gradient descent to this cost function, okay? And we'll try to minimize the cost function as a way to search for the appropriate weights to use in our model. Okay, so we'll apply a gradient descent to the cost function and try to find the correct weights for our model here. Okay. So, you know, artificial neural networks, so we'll start off with this kind of this simple toy example, and then well, I'm hoping we can do a cool example where you can use an artificial neural network for like handwriting recognition, okay? So you can feed into the neural network an image of someone's handwriting, and it will try to recognize the characters in the in that image. Okay, so it's very powerful and it's very cool, and it's just it's a very neat application of this gradient descent method here. Okay, so so I'll just put up some videos for you guys to watch over the weekend, and give you guys also some reading to do, and then we'll explore and try to do some coding here. The videos are Python based. I don't know if you guys are familiar with Python or not. We'll do the coding in R, but it's like the same thing. Okay. All right. So have a great weekend. Have a happy Valentine's Day, and enjoy your President's Day off.
Thanks.